Hello everyone, in this video I will be showing you the details on how to set up and use Coco Test Engine. This feature is part of Coco version 7 and onwards. If you want to upgrade or try out Coco, check the description below to get your hands on the latest installers. We will be replicating the steps of this tutorial, which you can find in the online documentation on doc.qt.io or bundled together with your installation. Today I will be showing you the setup on Windows, but similar steps should be available for Linux and macOS. The application under test we will be showing today is a parser example. This can be found in the SquishCoco installation directory. We first copy the parser subdirectory from SquishCoco to our own working directory. Then we can open this with our favorite editor or IDE. In this case, I will be using Visual Studio Code. Here you can see that Parser has several subdirectories, but we'll be focusing on Parser Coco Test Engine. Let's open Parser.h to see what the application does. So the program we'll be working on is a C++ expression parser. It can read a string and perform the indicated arithmetic operations on that string. It can also evaluate mathematical functions, and it can store results in variables. Now let's try to compile the parser example. A makefile called nmake.mak has been provided on Windows, and the corresponding file called gmake.mak is also provided for Linux and macOS. Using this makefile, we can compile this target executable called parser.exe. And we can do that using nmake. Now that we have compiled this application, we can execute it. And it now asks us to enter an expression and press enter to calculate the result. So we can start with 1 plus 2, or maybe evaluate one of the trigonometric functions, cosine of 0, and maybe use one of the variables that were named in the header file. In that case, that would be pi. Or maybe assign a value to a variable and use that variable in another calculation. Let's see what would happen if we had a typo, for example, XX instead of X. Then we can see that it also handles errors. So that was just a brief intro into the parser example, the application that we want to test. Now let's assume that this is the particular functionality that we want to validate. Here we have an input string containing an arithmetic expression and an output string containing either an answer or an error message. And we want to make sure that this output is correct with respect to some expected value. So if we go back to the header file that we looked at earlier, parser.h, we can find that this parsing functionality is provided by this class called parser, which has a method called parse, which returns an object of type parser result. And this parser result can be converted into a string using this MSG function, and this string returns either the error message or the result of the calculation. So this must be the function that we want to test. Now we can start writing tests for this function. In your copy of the source code, there is a file called testcases.cpp, which already contains a complete test script. What I will do in this video is to start from scratch and build up onto it or to something similar. Before we start writing a data-driven test, let's first prototype our test in a simple main function. First, we include parser.h. Then we write our main function, which will contain the body of our test. First, let's write the input expression, which is a string. And for now, let's assign a value of 1 plus 1. Next, we instantiate a parser object. And from this parser, we plug in the value of expression into the parse function that we saw earlier. And this returns if you recall, this returns a parser result from which we can obtain the error message or the resulting message using this MSG function. So we put .msg and we assign this whole thing to an output variable which we call result. Now we add a verification that this was indeed the expected outcome of parsing this expression. So we can check if the result is not equal to our expected outcome. And if we recall from the definition of parser, The answer has to be given by ANS equals the value of the result. So in this case 2. And we can verify this outcome. And if it fails, then we just, in our case, print an error message. In this case, it's the error of the comparison, and return a non-zero value. Otherwise, we return 0. Now let's try to compile this test executable. The compiler command is already provided for us by the make file, so we can just compile this target using nmake. Now we have our executable, and we can just execute it. And it didn't throw an error, and we can also check the return value, which was 0, so our answer is correct. So we were able to test the parse and message functions using 1 + 1 and 2 as our input and output values. But we want to be able to use the same test logic, but with different inputs and expected outputs. So now we can transform this simple test into a data-driven test. We can do this by using the macros provided by Coco Test Engine. Coco Test Engine provides header files that we can use to write the data-driven test. It can be found in the SquishCoco installation directory, which in my case is in drive C, program files, SquishCoco, under the include subdirectory. From this, we'll be using CocoTestEngine.h. The other files will be used in a different approach that is based on existing unit testing frameworks. So we need to include this header file, CocoTestEngine.h, in order to have access to some necessary macros. Going back to our code, first we include the header file, CocoTestEngine.h. Then we transform this main function into a test function using the CocoTest macro. This macro defines a test interface function that gets called multiple times, once for each set of inputs and outputs. The macro requires a name as argument, and this serves as a unique identifier for this test. This will be used to identify the files that contain configuration and test data later on. So for lack of a better name, let's just call it test name. In data-driven tests, the value of input and output variables are often stored in a separate table. This table is either defined in the source code or it is stored in some other file. So instead of writing the data directly, as we have done here, we fetch the input expression from this so-called table. We will define the table later on, but for now, we will use one of the macros, the CocoTestFetch macro, to fetch the value of this expression. The first argument is the type, which in this case is studstring, followed by the name of the variable. So this replaces this declaration. This declares a variable expression of type string and assigns it to the value stored in the table with the same name as this variable expression. After fetching the value for expression, we use it to execute the function to be tested. This leaves this part of the code unchanged. Then we now verify the correctness of the value of the string result using the CocoTestCheck macro. Its only argument is a variable to be checked, which in this case is result. This verifies that the value of result is the same as the expected output stored in the table with the same name as this variable. So this replaces this part of the code. The CocoTest macro defines a void function, so we have to remove this return call. Finally, the executable requires a custom main function, which we provide with the CocoTestMain macro. So this is generally how the test interface looks like. It begins with one or more calls to CocoTestFetch to declare some input variables and fetch their values from a table. This is followed by the execution of the function under test using the given inputs, and it ends with one or more calls to CocoTestCheck to verify the result against expected output values. You can also have multiple CocoTest declarations in one target program as long as they are each identified by unique test names. So now that we have completed our target program, we can recompile it to an executable using the makefile. Note that the SquishCoco include directory has to be added in the compile flags as well. This is already done in the makefile for us, so now we can call nmake. So we have now the test executable, which contains the abstract test case or the logic for executing the data-driven test, but we are still missing the test data. Going back to our source code, we declared a name inside CocoTest called testName. This is a unique identifier for this test, which will be used to locate the test data. When we execute this test, CocoTestEngine will try to find a JSON file called testname.data.json. This file is already provided together with the source code, so we can look at it here. So the file is in the JSON format. It has a top-level object which contains a member data, which has an array of objects. Each array item represents one set of inputs and outputs. Since this is a table, we call this one set of items a row of the test. For example, this first row contains an expression 3 plus 2, and the answer would be 5. Same for this one, we have cosine 0, and we expect the answer to be 1, and so on and so forth. To make it easier to view and edit this file, we provide a tool called Test Data Editor. So let's try to open this file with Test Data Editor instead. So this is how the data file looks like in Test Data Editor. So we have a tabular view of the file, and if we want to, we can even insert additional rows and fill up the values. So for example, earlier we had 1 plus 1, where the result was 2. Another thing to note here is this validated flag. It will become more important later on when we automatically generate test data. But for now, we can just think of this as a flag that says that this row has been manually checked for correctness. In this case, we know that this is the intended output, so we mark this row as validated. And we can save it and close Test Data Editor. Now we can run the test cases executable. And we can see that it ran the test called testName, which we have defined in our executable. And it executed 4 rows, and all of them have passed. So together, this test cases executable and this data file associated with testName comprise our data-driven test. In the previous section, we were able to write a data-driven test using the CocoTestEngine macros, and we viewed and edited the test data using Test Data Editor. In this section, we will be using CocoTestEngine to generate more test data that maximize code coverage. To do this, we need to define the generators that determine the possible values that our input parameter can take. This is done using a configuration file. This configuration file should be in the same directory as a data file. It has the same base name as the argument to the CocoTest macro, followed by .cfg.json. So for this example, the file name would be testname.cfg.json. And this file is already provided for us in the source code of the parser example. This file, which is also in the JSON format, contains a JSON object which has the fields inputs and outputs. The inputs field contains an object whose members are the names of variables declared in the CocoTest fetch macro. In our previous example, this would be the string expression. It has a string type, so we have chosen a generator of regexpstring, which is a regular expression generator. It has 2 required parameters, mean length and pattern. Pattern is of course the regular expression pattern that resulting strings have to match. Mean length, on the other hand, is the average length of the substring formed by the plus and star operators. In this case, we have a mean length of 10. The pattern for this example was chosen so that it generates the strings that are relevant to the function we are testing. In this case, these are just a combination of the mathematical functions and operators, as well as the numbers and variables. Outputs, on the other hand, just list down the names of variables that will appear in the CocoTest check macro. Now that we have our configuration file, it's time to prepare our target executable for test data discovery. The target executable, testcases.exe, that we compiled earlier, was only suitable for executing the tests. To enable test data discovery, the target executable should be instrumented with Coco's coverage scanner. This enables the measurement of code coverage as well as test data generation. In our parser example, this is achieved by calling the instrumented.bat script. What it does is it prepends the Visual Studio compiler wrapper of Coverage Scanner to the path so that Coverage Scanner is called instead of the Visual Studio CL compiler. It also sets the necessary arguments to coverage scanner. For example, CSON is for turning on the instrumentation. CSMCDC and CSMCC ensure that MCDC and MCC coverage levels are used for the instrumentation. And most importantly, CS test case generation activates the features needed for performing test data discovery. Finally, this script executes the arguments that are passed onto it. Before we use the instrumented script, let's first clean our build directory. Our make file has a target called dist_clean that we can use for this. So we can run nmake dist_clean, and this deletes our executables and other possible files that are created by the instrumentation. So now we can create an instrumented executable, which is one that can be used to measure code coverage. We use the instrumented script that I showed earlier and pass the entire nmake command as an argument onto it. In this case, we have the following command. Instrumented, so this one calls the instrumented.bat script, and we pass nmake as an argument onto it. This means that the nmake command will be executed with these environment variables, causing coverage scanner to be called with these command line arguments. So now we can run this command. So we see that coverage scanner successfully compiled our instrumented target executable because an instrumentation database or a CSMS file was also created alongside it. In fact, we can run this executable with our already available test data to measure the current code coverage of our data-driven test. So let's do that first. We run testcases.exe, and it produces the same output as before, but now it also creates an execution report given by this testcases.csx file that contains the code coverage measurement for this call to the test cases executable. To see the details of the code coverage report, we can open the CSMS and CSX files with Coverage Browser. With the -m flag, we give the name of the CSMS file, and with the -e flag, we give the name of the CSX file. And we see that 4 rows of our test data have been executed, and each one is recorded as a separate entry in the executions list. If we go to the executions pane of Coverage Browser and expand its contents, we can see that with 4 rows, we were able to reach 31.7% coverage. So if we want to increase this number even further, we can manually add more rows to our test data. But this is a time-consuming and tedious process. Instead, we can use the test data generation feature of Coco Test Engine to automatically discover test data that maximizes this code coverage. To do this, we need the Coco Test Engine executable. Like Test Data Editor, this is part of the Coco installation. So if you've set up Coco correctly, it should already be in your command line path variable. Let's run it first with the help option. The Coco Test Engine application is a driver tool. It drives the execution of the target executable that we compiled earlier. So we can supply the target executable with a -e flag. In our case, this will be testcases.exe. Then we can also supply the directory containing the data files and the configuration files. But since this is the current working directory already, and that is where we have the data files and the config files, we don't need to supply this argument. The next argument that we need is a test name. This is the same name that we supplied the CocoTest macro. In case we forgot them or want to know what are the test names contained in the executable, we can just use the -l or --list flag. So let's try that here. And this gives us only one test name, which is in this case also test name, because we only registered one test using the CocoTest macro in our executable. So we add this to our command line arguments. -t test name. By default, this command will just execute this particular test in this target executable using the existing rows in the data file. To activate test data discovery, we need to add the discover flag. Then we can customize the discovery process by first specifying the stopping condition. There are currently 3 of them. Max tries specifies a maximum number of rows that are tried. Max time specifies a timeout. And max coverage specifies a target coverage in %. For simplicity, we will use a max tries of 100,000. We can also provide an interval for printing status updates. And we can also provide an interval for periodically saving the discovered tests. So now we can execute this command which performs the test data discovery. So, after 100,000 tries, CocoTest Engine was able to find 76 rows with a total coverage of 81%. The new test data can be found in the same data file as before. We can now have a look at this data file again using Test Data Editor. CocoTest Engine was able to find simple, distinct valid cases, such as the empty expression, a single digit, or a simple function call, such as this factorial of 9. Recall that we had these 4 rows already at the beginning when we executed CocoTest Engine, so the genetic algorithm would have started with these 4 rows. And notice that 0 in parentheses and 9 in parentheses occur quite frequently in the generated input strings. So, CocoTest Engine could have discovered another test item by taking this square root of 9 plus tangent of 2 and crossing it over with the empty expression so that plus tan of 2 would have been removed, and then the remaining square root of 9 would have been mutated such that the function name would have been replaced by factorial, absolute value, or the logarithm functions. CocoTest Engine was also able to generate totally random looking inputs that generated error cases in the outputs. They come from combining the different function names and operators together, and these would have triggered different conditions and decision paths, which is why they were kept by the genetic algorithm. Now let's quickly talk about the validated flag. The outputs that we have here were only automatically generated based on the implementation in the source code. To make sure that the data that we have is suitable for testing purposes, we still need to validate each row. And that is what this validated column is for. Being validated means that we can say that this output is the intended output for this set of inputs, according to the specifications of this function. We can do this one row at a time, or we can also highlight the rows that need to be validated and use this validate rows mark as validated option. Together with the data file, a new CSEXIF file was also generated. So let's open that file with Coverage Browser. If we look at the executions pane again, we see that each of the new rows contributed around 10 to 30% coverage. But together, the entire test data allowed us to reach 81% coverage. This is because the genetic algorithm tries to minimize the coverage of every row while maximizing the coverage of the entire test data. To further improve the coverage, we can re-execute the test data discovery starting from the data file that we have generated, or we can manually add more test rows that we know will hit more instrumentation points. So let's have a look at the source code of parser.cpp and find where we can manually add more test data. So as you can see, the smaller equal to and the larger equal to operators were not covered by our tests. Thus, we can add new rows that try to cover these as well and see how that affects our code coverage. So first, let's rename this execution so we have a baseline for the comparison. Now let's open the data file again in Test Data Editor. And let's insert 2 new rows and add inputs that cover the less than or equal to and the greater than or equal to operators. Since we don't know the exact form of the result, we can use CocoTest Engine and instead learn it. This can be done using the learn flag. This means that we execute the inputs and overwrite the expected outputs with actual outputs from the implementation. As we can see, learn mode updated 2 rows of the test data. Now let's view the updated test data. And the result column now contains the expected answer, which is true for the first statement and false for the second. Let's mark these as validated as well. And let's re-execute the data-driven test. This can also be done with CocoTest Engine by just providing the executable name and the test name with no additional flags. So all of the rows passed as expected, and this also generated coverage data, which we can view again with Coverage Browser. Let's look at the source code again. So those additional rows now cover the instrumentation points for the smaller equal and larger equal to operators, and we've increased the coverage incrementally to 82.6%. We can even further improve the coverage by running test data discovery once more, starting from the 78 rows that we already have. And after a few minutes, it was able to find new rows that improved the coverage further to 87%. So that was Coco Test Engine and test data generation in action. For more details on Coco Test Engine and Coco in general, please visit our documentation page on doc.qt.io, linked in the description below. Thank you for watching.